Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is a TEGAM? I actually don't know how to say that. A Nullmeter AVM-2000, a fairly sensitive one that can operate down to nano-Volt range. I'm not sure if I've covered Nullmeters on the channel before, but to put it simply, they provide very good high input impedance, very low noise front end, allowing you to measure differences down to the nanovolts between the two inputs. It has a fairly large analog display, a LCD screen, and unfortunately this unit is faulty, and we need to see if we can fix it. Now, nanometers, because of their low noise nature, often operate from an internal battery. That also makes them completely floating and isolated from everything else, and this one, of course, is no exception. Unfortunately, the designers have chosen such that if the internal battery doesn't work anymore, you cannot use this device at all, even with an external power source. It will just simply give you an error. You have to fix the internal battery, and it comes with a 6-volt lead-acid battery. Not an expensive change, but we're going to have to open this up and remove the battery and find a way to hack over that, because as I plug it in, you can see what happens with the battery being dead. There you go. So even though it's actually turned off, it does come on trying to charge the battery, and it says error. And with this error, nothing you can do. And this is a normal behavior. That's actually not what's wrong with this unit. Something else is going on with it. So we have to open it up anyway. And the back of the unit is pretty boring. It does have the DC input, a fuse, and the isolated output. Now, this analog isolated output is very helpful because essentially you can use this instrument as a low noise preamplifier in that case, not using the front panel analog display. So you can adjust the gain of this by adjusting the range, and then you get a super low noise front end, which is nice. And here's what's inside of the instrument with the top cover up. You can see I've already removed the battery, which sits in this little compartment over here. So we can put that aside, and we have to recycle this carefully. These are lead-acid batteries. And then I just made this little converter here. This is just simply a 7.4 volt lithium battery that we can put in there just so we can power this on. Now the voltage of this is higher than the voltage of the battery, so we are not in danger of, let's say, overcharging it because of the power supply connected. And we also have no problem because this has a wide input range and it can operate from a wide range of supplies. So this should be enough to get us over the hump. And while we're in here, we can take a close look and see what's going on. So they're passing the voltage at the preamplifier output in the back through this cable, and that's what that ferrite is most likely for. And then the power supply comes in here and goes this way, and then the voltage comes back that way. So there's a few back and forths here, and they've tied it all up together. Nothing unusual, I don't think, on this. Just a couple of protection diodes, some voltage regulators, and some pot to adjust the turnover point between the battery and the external power supply. And the front of the unit is a little bit more interesting because we do have a processor here on this one, which of course controls the display. We do have the analog meter movement in here, which is driven directly from this board as well. And there is a bunch of cables here that go into this enclosure here, which is where all the analog stuff is, which probably we're going to have to take a look at depending on what's wrong with it. But looking at this, I don't see any coaxial connections anywhere in here. So I wonder what interfaces they're using between what's inside of here and what's in there, because the input is being taken from the front directly through here. There's actually cable in here that goes in there, which you probably saw when we were looking from the top. But now we have everything that we should at least be able to turn it on and see how it behaves. Okay, with our temporary battery, let's plug it in, and hopefully that error should be gone. Let's see what it says now. And there you go. It says charging. Of course, it's not charging because it's already way over the battery, a lead-acid voltage battery, but it thinks it's charging. But it does show that the battery is full, which is consistent. So I think the battery stuff is now working. Let's now turn it on. Okay, there you go. Self-test. Not a bad sign. No movement or anything yet. I wonder if this self-test completes and if it returns any errors. No errors. Okay, so we have a lot of stuff on the display. We have a range of 100 millivolt. Nice, I can change the range. Let's put it on 3 volt. We have an impedance 10 mega ohm, and I think I can change the impedance. No, that's 0 and operate. There you go, 110. We can go between 100 and 10, and then we can dial in an offset. You can see how small, how many digits there are in the microvolts for the offset. That is, of course, for being able to measure those extremely small nanovolt range inputs. And there's a digital filter over here, 0.1 second. So we'll get into its operation in a second, but there's a way to check to see if the analog meter is working. If you hold this button in the front, it gets into this other menu, which is like the calibration and adjustment menu. So if I go over here, look at that, the meter does move. So this should be full scale on the positive side. One more, full scale on the negative side. Yeah, it looks actually pretty close to where it should be. And then there is output offset adjustment, zeroing, and there's an internal voltage reference actually in there, 2.667, which you can use for measuring. And if I press that back, it goes back. Okay, so far so good. Let's go ahead and put an input on there and see if we can measure anything. So now I have a very simple setup here. This is a 5 volt standard voltage reference that we can feed directly to the inputs. So let me set the range here to, let's say, 10 volts. So at 10 volt with 5 volt coming in, it should be exactly midway. So let's try that. I'm going to turn it on. And Nothing. Nothing happens. No movement at all. That's unfortunate. So if we go this way, 30, 100, 300, 1,000. So look at that. This goes all the way up to 1,000 volts, but then there's no movement on this display at all. Now we know this worked because I tested it before. At 1 volt, it should be completely railed. No, there's nothing. Let me turn this off. Now if I keep going down, here's 300 millivolt, 110 millivolt. Look at that, 300 microvolt. And it keeps going down. Nanovolt, 100 nanovolt. So from 100 nanovolt to 1,000 volt, that's a big dynamic range. But at 100 nanovolt, when when things are just wired, it should be slamming left and right, because there's 100 nanovolt can easily be achieved. If I disconnect this and touch this, it should go wild. So yeah, there's nothing. Now, so it's not working on any of the ranges, which is a little bit unusual. So something has gone catastrophically wrong with it. I think it's time to take a look at this architecture, because we need to understand how it is built before we start taking it completely apart. And a quick search online, we can find a manual which has a really nice block diagram, and it has the schematic, which is fantastic because we can really dig in now. Now, if you look at this, there are 3 main sections, and we've already seen 2 of them, which is the battery section as well as the front panel. And we'll talk about each of those individually. So here's the battery charger section. Here's the 6-volt lead-acid battery, which we've already replaced with something else. So this is all working because the unit turns on, which means there's definitely power being delivered to this front panel subsystem. Now, before we talk about this, it makes more sense to talk about the analog subsystem first. Now, this is an entirely isolated section. And we can see this, of course, it says this is an isolated section, but it's galvanically isolated. It still needs power, so they have some kind of a DC-DC converter here across this port to power this entire section internally, some kind of a switching power supply. And then they have optically isolated serial links. This also tells us that all the information about analog measurements are sent to the front panel via a digital interface. And that's why they have digital to analog converters, 20 bits in here, and they have 24-bit analog to digital converter in here. So it's kind of funny because you're applying an analog signal, becomes digital, becomes analog before it's displayed again. So the little isolated outputs in the back are also driven from a 20-bit digital to analog converter. And the little analog display needle thing in the front, that's also driven by something like that. So it's an interesting architecture in that regard. And multiple different power supply sections, 5 volt here, 5 volt analog and digital. Here's plus and minus 12 volt analog, and here's more power supply. So they have taken a lot of care to make sure they isolate those. So I assume that some of these are regulators in order to be really low noise and have good power supply rejection, and this has to be switching because you're going across an interface. So the input coming in, the high and the low, goes through this input attenuator, and that makes sense because you attenuate the voltage, especially the 1,000 volt, in order to make it compatible with some kind of an amplifier front end. And when you're measuring something really, really small, you have no attenuation, and then you're going directly into the low noise amplifier, which is very high impedance at the same time, allows you then to low noise amplify the signal. So it looks like that this front end can do times 1, times 10, times 100, and 1,000. And it goes into some low-pass filter, which is necessary because this is really a DC instrument. And interestingly enough, it generates 2 outputs, a times 1 and a times 10. And they both go into this thing, which I'm assuming is a chip that has all these peripherals on it. It has an 8051 microprocessor, it has yours, it has DACs and ADCs. And the DACs are used to come back and create offsets to do some offset compensation. So lots of stuff is happening here. And the data that's interpreted is sent over here. Then this guy receives it, this microprocessor receives it, and it converts it back into analog. And then at the same time, any range changes would have to go this way because you need to control all of these input attenuators, apply offsets, and everything else. So there's a lot of stuff going back and forth. So right now, the symptom is that we know that this stuff works in the front, or at least the needle works, because that means that this 20-bit analog to digital converter digital to analog converter must be working. Otherwise, you wouldn't be able to get that. So there is something going on here. The front panel definitely is working, but then on the other side, none of these ranges work. So it almost looks like the input is not connected at all, because no matter what I do, nothing happens. Now you may say, well, maybe one of these wires is broken. But even if the wire was broken on the 100 nanovolt range, you should see this needle move because there's enough noise in the system to provide some kind of drift and movement. So something else is going on, something a little bit more maybe fundamental. But nonetheless, it's important to look at this. So I suggest that we take a quick look at the schematic and find out if there is any place we can measure things and apply a signal and see if we can see any analog activity in here before we dig into anything else. And the schematic is really good. It has tons and tons of information. Now, interestingly, this instrument was made by PPM originally in Cleveland, Ohio, and it's from almost 19 years ago, and it must have been bought by another company, and that's why the branding is different, I think. So if you look at this, this is the power supply portion of the isolated analog board, and there's a lot we can learn from this very quickly. First of all, we see the serial port interface. So this must be where the instrument sends the digitized data back onto the front panel, which then uses DACs to display them. But there's also a single power supply coming over here, and it goes into this module. And this module is a DC-DC converter. Single voltage comes in, plus and minus 15 go out. And this is where the galvanic isolation actually is around through this little component here. Now these are going to be noisy still, because they're switching power supplies, and they pass them through some voltage regulators. That's how they get minus 12 and get a plus 12. And there's some other voltages generated here. Interestingly enough, it looks like you can also generate 2.5 volts for the reference of the ADC with an external part with the jumper, so it's probably either populated or not. But nothing unusual here. We should certainly measure these power supplies, because without them, of course, nothing will work. So this would be the first place to check. Now, if you go further, we will very quickly get to the attenuator. So that front-end attenuator with all the different switches to control various attenuation is done with all these relays. So all the relays are going to switch in various resistors, and that's how they get the attenuation going. And these are the drivers for the coils of all the relays. It looks messy, but in reality, it's really not doing anything other than providing all that attenuation. And there is a core amplifier that generates the amplified signal. Everything else is just switches. And there's some offsets coming here. These offsets are for canceling the input offset. You can see that they go into the core of this front end. And there's two other amplifiers in here, which are connected back to back with a diode, and then they go through this bipolar. These might be overrange detectors, because if this one is active, it can pull down. If this one is active, it can also pull down. So I think they're just probably, if this signal is pulled, it means it's an overranged. Maybe then it will kick in, for example, some protection if you connect like 100 volts when you're in the 1 volt range. So nothing unusual here. Of course, if any of these is broken, it wouldn't work. But the reason I'm reluctant to blame any of this immediately, the power supply is different, but you should still see some movement, because there should be noise on the 100 nanovolt. That's what puzzles me, why there's absolutely no activity at all. Now, of course, one possibility is that the serial connection actually is broken. That would be one way to see no activity, because we know that the digitized data needs to go to the DAC. Now, if I keep going, what else do we have? So this is the remaining amplifier. There you go. So here's the amplified signal. And then it goes through this filter. And then we have some more offsets. Here you go. References and DACs coming in. And it comes into 2 points. There it is. Here's the two analog signals. Here's one here and here. Look, there are even test points. Fantastic. We can easily measure these test points to see if they're working or not. So these must be the two signals going into the microprocessor for digitization for the 24-bit ADC. So the signal flow, the signal path, pun intended, should now be obvious. And then we're looking for these two signals to see if the analog front end is working. And let's see what do we have here. This is, I think this is must be the microprocessor. Yeah, it has to be. There's some programming port. There is a crystal. Here's all the signals to control the relays. That makes sense. And here is there it is. Here's the digital data coming out. So here's a serial UART port coming from this opto-isolated. So here's our second galvanic isolation to the opto-isolator section. And here are the analog signals. There it is. And they go into the analog inputs. There you go. So the signal is now clearly going in here and getting digitized. That makes sense. Nothing strange there. What else do we have? Front panel switch and so on. Not very interesting. And here is the front panel display, and this must be the 18F452 from Microchip. That must be what is driving, what's communicating with the analog board through the digital interface. So that those digital bits must be coming in here somehow, connecting to this. I don't know where they're coming from, but they must be here somewhere. And what else is there? Here's the DACs. Yeah, so this guy doesn't have DACs inside, certainly not 24-bit ones or 20-bit ones. And it's sending the signal into this, and this must be the real panel BNC connector. And here's the meter. Yeah, you need an op amp to drive the meter. Looks good. What else is in here? This is some kind of, this is the input coming in. Yeah, that's the charger and everything else in the battery. Yeah, so now we have so much information. The schematic helps so much, because we should be able to measure. Our first action should be to go all the way back here, measure the power supplies, of course. If the power supplies are working, go ahead and monitor the analog voltages and see if they are working or not. And if they are working still, then we can monitor also the digital interface. So we have a sequence of things to do. And here's what the analog section looks like with the cover off. And by the way, check out this cover. Look at the size of this, a few pounds of aluminum for sure. And now that we've looked at the schematic, we can very quickly identify the key elements here. So here are all the relays that are responsible for switching the attenuation. Here are the drivers for them. And here's the analog section. Over here, here's the power supply coming in. This is that little module that generates plus and minus 15. Additional filtering. Here's some section for our regulator. And then here's the microprocessor that has the ADC and everything else in it. Here's the optocouplers underneath this cable. There you go. You can see them. Yeah, so it's actually pretty straightforward once you have the schematic. And all the little test points are there. So we can very quickly measure all the power supplies. And then my plan is to apply a 1 hertz sinusoid to the input. This is the input signal coming over here. If I apply a 1 volt peak to peak 1 hertz signal, we can then go all the way at the output of this entire section and measure it backwards. If the signals are already there and they change when we change the range, that's a huge debugging step already, because that tells us a lot about what's going on. And if that step doesn't work, we go backwards. Of course, if the power supply doesn't work, that's probably the luckiest case, because the power supply would be the easiest to fix. And yes, it is true that without any power supply here, we would see complete silence from everything else, because there would be nothing created, no digital signal going out. So that hopefully is the problem. We have a secret attacker waiting. Pooch, do you think it's a power supply problem? Okay, let's do some power supply measurement here. We have multiple domains. That's from the digital one. There should be 3 volts, otherwise the microprocessor won't work. No, we do have the 3 volt. There should be a 5 point something here. Yeah, that's working. Let's look at the analog domain. There should be plus 12. Here's plus 12. There should be minus 12. Minus 12. Well, unfortunately, those are all there. What about our 2.5 volt reference for the ADC? Where would that be? Around here, I think. Here it is. Is that there? And that's there also. Okay, so the power supplies are good. Now we need to look at the analog flow. Pooch, what happened to your CAT scan skills? You told me the power supplies were bad. They're perfectly working. I'm paying you too much. So let's do some analog measurements now, since the power supplies are working. I have connected 2 channels of an oscilloscope to the end of the analog line. Those are the 2 inputs that go directly to the microprocessor. The nice thing about measuring those is that you'll be measuring everything. All the op-amps, the attenuators, the switches, everything has to be working for that to actually operate. So if that doesn't work, we can start working backwards and finding the fault. Now, at the same time, when I do this, I can actually change the settings, and then the amplitudes should change, because we have a ×1 and a ×10 input, so they should already be different, and they should be centered at around 2.5 volts. Now, to make that measurement, I'm going to use the Keysight HD304 MSO. This is the 1 GHz 14-bit oscilloscope. This has the smoothest interface I have ever used, ridiculously fast. But in roll mode and at the 5 MHz bandwidth, it would have a 16-bit resolution, extremely low noise and very high dynamic range. So it's perfect for an application like this. It also has a built-in generator, which I'm using to feed directly to the input. There's a cable here that goes in, and I'm actually feeding it directly in here, and we're giving it a 1 hertz, 1 volt peak-to-peak signal. So everything is basically encapsulated in one setup. The generator is turned off, so we see nothing, but we do see the voltage there. So let's take a closer look. So here the instrument is in roll mode, and you can see that I have entered an offset on both of the channels, an offset of 2.5 volt here. On channel 1, 5 MHz, 16 bits, and it's in a 50 millivolt per division here, and on this one, 2.5 volt, and 100 millivolt per division. So we expect these voltages to have some activity when we apply a signal. Now there's a bug, I think, in the software here, because I don't see any of the labels anymore. When you put it into roll mode, the labels disappear. They absolutely have to fix that. That's pretty annoying. So if you go over here and turn on the source, let's see if anything comes out here. I have set up the source to generate 1 hertz, 1 volt peak to peak. Is there a signal? And look at that, there is. The analog front end is actually generating and passing that 1 hertz sinusoid. By the way, you may ask, why am I using 1 hertz and not higher? That's because this is a very low frequency front end. There's a big filter in there, so you don't want to apply high frequency signal to it. But yeah, it's working. So now if I go ahead and change, for example, the scale at the input, let's see if that makes any difference. If we can make this any larger. Yeah, look at that, it works. Yeah, I just changed the scale and I made it larger. If I go even any lower than that, at some point, there you go, it's even now, it's railing very, very hard. Let's go the other way. So we're back to this. At some point, it should become smaller if the range is even larger. There you go, it does. Yeah, so it's working. This is really surprising, because this signal is directly applied to the data converter. There's nothing else between what I'm measuring and the input of that chip. Now it's a bit problematic, because I'm getting nothing, so the only thing left is the serial interface, if that's not working. But the serial interface must be working at least in one way because we can change the range. So that's also puzzling. Maybe the ADC is dead, but that would be surprising too because there's 2 inputs. Anyway, the mystery continues. Well, let's do one thing at a time. Let's go and measure those serial interfaces. By the way, I also checked the analog output in the back. There's also absolutely no activity on that one neither. So they are basically both doing exactly the same thing, which is consistent with no data arriving to the front panel, because the front panel uses one DAC here and one DAC here, and neither of them are doing anything. So now the next logical step would be to monitor the signals going from the front panel into the analog board and vice versa. This will be the digital interface. Now the first thing would be to measure it from the front panel, because we know that should be working, because if it wasn't working, we wouldn't be able to change the ranges. So let's verify that. I'm going to find that pin over here and connect that. And take a look. There's a whole bunch of digital activity going on. So the system is constantly sending the state of the attenuators and the relays and offset with a long set of data into the analog board. So if that wasn't working, we couldn't change the range. But look, if I change the range, look carefully, you can see some of the bits shift. You see that? And you can even see that little LED on the analog board blinking, which I guess it's like an acknowledgement. So yeah, it is working. That makes sense. Now let's look at it the other way around. That's the signal coming from the analog board into the front panel. That's the one that's supposed to move the needle and supposed to do everything else. That's what's going to the DAC. If I go here, let me see if I can catch that signal. Here it is. Look, it's doing something. It's actually sending data. But no matter what I do, these bits never change. So I can turn the generator on and off. Nothing. I can change the front range. Nothing. It comes and goes, but it's always the same set of data. So this data must obviously mean nothing because it's not moving anything, it's not generating any voltage, it might be clamped at the lowest value. I don't know, but this is quite mysterious, because why wouldn't the processor send the right data? If the analog voltage is sitting at the DAC, at the ADC input, why is it not doing anything? That's really bizarre. So now I'm beginning to wonder if there is a corrupted firmware going on, because this chip runs a lot of stuff, and if its firmware has been corrupted, maybe that's what's preventing it from reading the ADCs correctly. There's even a programming header, and we're going to take a look at the datasheet of this part. You can program it through a serial interface also, but we're going to, of course, need the program to program it. So I'm going to reach out to the company and see if they can send me the hex file. In the meantime, let's take a look at the actual block diagram and what's going on inside of that chip. And here's the datasheet for that part. It's a pretty cool chip. It's got some really high precision ADCs and DACs inside. It's from Burr Brown, and its application is exactly things like that data acquisition and so on. But because it has an 8051 microcontroller on top and a flash memory inside, it's kind of an SoC, has everything in there. You can do a lot with it. And here's what the chip looks like. It does have an analog mux in the front to switch various inputs into a selectable buffer and a programmable gain amplifier ultimately into the modulator. So it does have a lot of analog inputs. It can measure them all at the same time, of course. But it has a lot of other things like DACs. It has a built-in reference, a lot of offset correction, and it does have this processor inside. So the flash memory that's in here somewhere, there it is, that flash memory and the SRAM and everything, they all work together just like a regular processor would. And if this is corrupted, yeah, you wouldn't be able to read the right thing, and you wouldn't be able to send it out through this. It's a really bizarre problem, but it's really my last hope that the firmware is the issue. But overall, it's a pretty interesting part. Well, there's some bad news, unfortunately. So TEGAM is now part of a different company called Advanced Energy. And I reached out to them, and they will not share the hex file of this with me. Even though this instrument is 19 years old and is obsolete and they don't make it anymore, they will not share that. But they did offer to take a look at it for me for $500 and fix it for $2,500, which of course we're not going to do. It's a little disappointing because that hex file is useless for anything else, but it could have revived this if that's the problem, in fact. So we're going to have to look for a different solution. Now, I really want to contrast how Advanced Energy treated this customer support problem compared to something like Associated Research. I repaired this on the channel a while ago, and I bought this as a broken item from eBay, and it was missing a board. And when I reached out to Associated Research, they said, sure, we'll give you the board that's missing. And they charged me only for the cost of the parts on that board. They even shared with me all the instructions on exactly how to put it back and get it up and running. And this is not an obsolete unit. This is their flagship Hypo Ultra unit. So they basically did this for me just so that we could recover this. And they had no idea I was going to record this. But yeah, Advanced Energy, they just simply completely turned it down. So there's something to be said about good customer support. And interestingly enough, if you go to the TEGAM website and download the manual for this instrument, the schematic is gone and the block diagram stuff is no longer in the manual, which is unfortunate because the old version of the manual, which is still luckily available to download, has all that information in it. Well, after a tremendous amount of searching online, I finally managed to get in contact with somebody who could download the hex file of a working unit and share it with me. I also made my own little board to extract the firmware from this one, which is done through the serial port, and I'll show you the software that I found for it, and you can just download this out. Now we can compare the hex file from this one and the hex file from a supposedly working unit, hopefully a similar version, and see if there's actually any difference between them, and then maybe download that one back into this and see if that fixes the problem or not. It's a long shot, but it's worth a try. Okay, so I use this little program to read the hex file and similarly from a working unit, and let's see if we can compare those two files here, just using some random online one. So here's on the left from a good one, and here on the right is going to be the from my unit, the one that's not working. There we go, and let's see if there are any differences between them. Looks the same at the top. All right, so it found quite a bit of differences between them. Interesting, there's a lot. Let's show only the differences. And what do we have here? Look at that, there is a section missing. That is really interesting. Actually, you know what, let's just look at the whole file. Let's scroll down. Can I move this around? This is a really not a very good way to display this, but let's see. This all looks the same. Wow, there is a chunk missing from my unit. That must be corrupted or erased. That is so weird. Yeah, so from this memory location to this memory location, I have nothing. But there was a lot of differences. There were a lot more differences. Look at these are all identical. And keep going. Oh yeah, and at the end it's all different. But you know, I think this end part is maybe just calibration coefficients. Like these parts over here, they're probably not part of the main program. It has to be that. Yeah, these must be constant because they're all so very different from each other. I mean, some of them are similar, but then, yeah, this has to be calibration. So maybe we don't overwrite this part. I actually don't know how to not do this part. Maybe we can just cut it out of the hex file. I mean, what's the worst that can happen? You can always reprogram it with the original file. But this gives me more hope because having a chunk missing, wow, that might be it. That would be really cool if this really fixes the problem. Okay, well, let's hook it up and program the chip. So I copied the portion of the file which I think is the calibration coefficients back onto another one and made a new modified file. Now the difference between them is purely the missing part. I've configured things, I think, correctly. Let's go ahead and see what happens if I go download. All right. Well, it's doing something. Now let's see what happens after this is completed. This is a normal procedure. At the beginning, it's setting up the clock and the registers and everything else. Now the moment of truth. And it is done. And check it out. If I go to lower ranges with nothing connected, it begins to saturate. It is working exactly like we thought, because even a little bit of voltage is enough to saturate this under low settings like the millivolts to the microvolts. Yeah, that's amazing. So the communication is obviously not working because this is moving. So that's a huge leap forward. Now we need to do a quick calibration and then see if it actually measures anything correctly. But that's pretty awesome. Okay, let's do some verification here. So I have the unit connected at the back, the analog output. All the way back there is connected to an Azure 8.5-digit multimeter. And then the input is coming all the way up there from a crown height voltage reference. It's a precision DC source. So we should be able to apply an appropriate voltage to it. And then let's see if it does anything meaningful. So I'm trying to keep both of these instruments in focus because they're at very different depths here, but I have done the calibration as well as the zeroing of this and everything else. So let's go ahead and measure something. So we're at a 100 volt range. Let's apply 100 volts, and that should be a nice full scale input. Here we go. Let's settle. The filter is on 2 seconds. There you go, not too bad. We're reading 0.992 or so. There's going to be some offset here which needs to be corrected for full calibration. But it is definitely working. It's good enough for this purpose. So now let's go ahead and put this to, let's say, 10 volts. Okay, and the 100 volt range, you should be just a very small reading here. There it is, 0.95. You can see the offset is actually the same in all the ranges, which is good. So now on a 10 volt here, this should be now full scale. And it is without issues. Let's try 5 volts here. It should be nice and midway. Look at that. That's pretty good. I would say it's working nicely. Let's go really small. Let's try 1 millivolt, which is a huge drop here. And a 3 millivolt range here. Look at that. I'd say that's really nice. So the 0.32 that you see, you have to divide that by 3, of course, and it's pretty close. You can see it has roughly the same offset in every range, which is good. Let's try 0.1 millivolt here, and let's go into, let's say, that's going to be full scale. Let's try here. Let's see where it goes, and it should be full scale here, and it is. Looking really good. Now, if you want to go lower than this, we have to be a little bit careful, and I'll show you why. So at the really low inputs, this instrument is actually constantly flipping the polarity of the input. There's a relay that does plus minus, and that allows the instrument to remove the inherent offsets, which is quite good. This is done at very, very low voltages because any EMF from the connectors is going to overwhelm the instrument otherwise. So let's set our crown height source to exactly 0, right? So now the display of the crown height says 0, and you would expect it to put out 0. Of course, it's not going to. So let's go down, get in range here. Here's a 300 nanovolt range. You can see that it just saturates it. So the voltage coming out is already larger than 300 nanovolt, even though we've set it to 0. So let's go over 1 microvolt here. Let's see how much offset does it have. Yeah, you can see the offset is quite large. It's even more than that. 3 microvolt. Let's see where it stops here at some point. There it is. Okay, so that's the inherent offset directly from the crown height source. But we can zero that and then see if we can measure 1 microvolt. That should be interesting. So I have an offset control over here. So we need a negative offset. So here's -1. Not quite enough. Let's see. A little bit more. I still need a bit more. Let's see, is that at 0? Or did I do too much? That's, I'd say it's pretty close to 0. So which means that the instrument is generating -1.5 microvolt, and I'm combating that using this input here. So now let me apply 1 microvolt from the crown height, and let's see if it can measure that. 1 microvolt. And look at that. Let's see if it settles to a rough value here. Look at that. That's pretty amazing, right? So I can measure 1 microvolt on top of the 1.5 microvolt offset that the instrument already has. Remember, that's not from this. That's actually from the crown height. I've verified this using a different instrument, that offset is inherent to the crown height instrument. So pretty impressive. So now if I go to the 1 microvolt here, it should be nice and full scale. And it is almost there. There might be a little bit additional offset from this instrument as well. Let me set the crown height back to 0 again. Here we go. Let's see where this settles. If it settles at 0 or not. Yeah, you can see there's a little bit of an additional offset here. So we have to fix that. 4 and 3. Now we're correcting the instrument itself. Let's see. Yeah, pretty close. At this point, even just me bringing my hand close is going to change this because I don't have the guard connected. Okay, now let's go to back to 1 microvolt. And it should be nice and full scale. There it is. Look at that. Pretty good. So normally when you want to make measurements like this, you do have to use a bridge. Yeah, you can see just me moving around, moves it around, and it needs a guard voltage. With a proper Kelvin-Varley voltage divider bridge, we should be able to make these measurements without any issues. And I should make a video separately about that because I do have one all the way up there somewhere. Yeah, there it is up there. You can see it and Teardown from the top. So we could potentially use that to make these divisions as well. But yeah, I think this is working quite nicely. There's a lot of cool experiments we can do with an instrument like this. And let me show you something else. I have 2 thermocouples here, these two. I have shared their negative terminal, and I'm connecting their positive terminals between the low and the high input of this instrument. So basically, I'm subtracting the voltage generated from these 2 thermocouples, which means that if one of them is hotter than the other one, the needle should move towards it. And if the other one is hotter, it should move the other way. So I'm just going to touch one of them. Look, I'm going to warm up this one. Look. The needle moves that way because there's a temperature delta between them. If you wait long enough, it's going to come back because the temperature is going to equalize. But if I touch the other one, I'm going to make the other side hotter, and it's going to move in the other direction. So you can see how using a null meter and using 2 thermocouples, you can actually measure extremely accurately the temperature differences between 2 nodes and offset, remove everything else from that. And of course, the common mode here, the common mode temperature doesn't matter. You're really only measuring the delta. And even in this crude setup on a 1 millivolt range, this is easily measurable. And there you have it. I hope you enjoyed this detailed repair and experiments using this null meter. As always, thanks to the Patreon and PayPal supporters. You really make this possible and being able to purchase these instruments and do all kind of experiments with them. If you have any questions, let me know in the comment section, and I'll see you next time.